Me kids, look at me getting a video of myself into PowerPoint. I could not be more proud of myself, but I'm sure to mess it up as we go along. Anyway, thank you for watching these videos while my family and I enjoy Devin's, our daughter's wedding festivities these next couple of days. So I really appreciate it. And hopefully this goes okay for you. All right, so the first thing we're going to do here, this warm-up, is number one really is a warm-up leading into what we're going to be do today, and two is a review of yesterday. So pause the video if you want and see if you can do the warm-up by yourself. If you remember, if not, that's okay, just go along with me. If you remember from single variable calculus, if I know that the first derivative is equal to 0, I know I have a horizontal tangent, but I don't know about that's not enough to say I have a local max or a min. I can do a number line test in single variable. Spoiler alert, that doesn't exist in multivariable, but the second derivative test has an analogous, whatever, has something similar in multivariable. So to review the second derivative test for extrema, remember that at a point, if you know that your second derivative is also negative, you know you're concave down, and if you have a horizontal tangent, then you must have a local max. However, if you have the first derivative equal to 0, meaning you have a horizontal tangent, and you know your second derivative is positive, you're concave up at that place where you've got a horizontal tangent, and that means you've passed through a local, min. And do you remember about if they're both 0, what conclusion we can make? None, right? And so in single variable, this is inconclusive. No conclusion can be made. In single variable, we then default back to our first derivative test. That won't happen to us in multivariable. We will always be able to make a conclusion, not testing about when you can't. All right, so the directional derivative. Remember, for the directional derivative, you have some surface, right? You have some surface in the xy plane described by x over y, and there's a point in the domain, 6, -2, right? That puts me on this surface, and I want to know if I walk in the direction that they're telling me, -1, 3, am I going to, right, with that, the shadow of -1, 3, right, is down here on the xy plane, and I want to know if I move in that direction, does the z height go up, down, or stay the same? So that's what the directional derivative is telling us. And now if you remember how we compute the directional derivative, we need the information we have. And first we need to get the gradient, right? The gradient of f. So that's just my partials. And I have what? 1 over y and negative x over y squared. And at my 0.62, what is that? At my 0.62, -1/2 and -3/2. I think if I do that math right, let me check my notes. Yep, that's what I have. And then remember, you're going to, in order to get the directional derivative, you need the unit vector that goes with our direction vector dotted with the grad that we just found, grad f. So we have -1/2, -3/2, dotted with -1, 3. But up here, I need to find the magnitude of that unit vector, which is just the square root of -1 squared plus 3 squared, so the square root of 10. And I suggest that we keep that out here. So I do that dot product, and I ended up with a -4 over root 10, which means at the point on the surface where 6 is -2, so that means at f of xy, whoops, I should have said 6 -2, which equals what? -3. So at the point 6, -2, -3, if you move in the direction of -1, 3, your height is going down. All right, good. so let's move to today's lesson about finding extrema. So finding extrema is going to take us actually 3 days, 3 lessons really. 14.7 is finding local and then finding absolute. I'm going to break that up into 2 days where we're going to just do local today. And then the next lesson will be finding absolute. And then the last lesson of the chapter will be using a different technique to find absolute maxes and mins given a portion of our surface. So you should have a note sheet that the sub has given you. Definitions of max and mins, the same as it was in single variable. Remember, we're only going to talk about relative or local maxes and mins today. So if you have a minimum, it means like all the y values on the surface near our point all are bigger, as opposed to a relative max is if I'm on my surface, all the points in a local area, all those points have z values that are less than or equal to our point. So here's a nice little picture of a 3D surface and a little snapshot of it, and you can see a local maximum and then a global or an absolute maximum along with a global min. Again, today we're just going to be identifying either the spots or the critical points where these will exist, and then if we're asked to classify them as local maxes and mins, we are not going to consider their heights and see if we have any absolutes. So here we go. Remember, first, if you're just asked to identify a critical point, we then would move to the first or second derivative test for extrema, and it was like the critical points were our suspects, right? Who and where should we be looking at? And in single variable, that was where the first derivative at a certain x value was in the domain was 0 or does not exist. And I had to make a big deal about remembering also when the derivative does not exist. So now, what do you think? Right? It's just not the derivative, but the partial derivatives, right? So in order for, if you have 2 independent variables, to be a critical point, and also, UMD and the book likes to call them stationary points, are if both partials are equal to 0, not just one. Both of them have to be equal to 0 simultaneously, or one of the other has to not exist. We're not going to really do those. We're going to be dealing with nice smooth surfaces. So we really are just going to be dealing with setting the partials equal to 0. So in multivariable, when you have your domain being the xy is what we're going to be dealing with, and our height being so we can see it in 3D. A critical point or a stationary point can either be local extrema, or they can be something called a saddle point. That's right, a saddle point. So there I have a couple of pictures of where you see some local mins, also I guess global there, and then some maximums, if you can see the 2 pictures here. And it's kind of like, think about it as like all the concavity is in agreement here, right? In here, all the concavity is in agreement around these points. And the same here, right? All the concavity is in agreement. But look about here, it's like the concavity can't make up its mind. Am I concave down right here, right here? Am I concave up right here? What about on this path, right? It's kind of like a point of inflection where it's like, well, I think I'm going to be, no, I'm not, right? So those are called saddle points. They generally come from our hyperbolic paraboloid functions in 3D. So I like my little picture of a saddle though. And remember, let me go back for a second. Oh, I guess it doesn't let me go back. There is no first derivative. There is no analogy to the first derivative test in multivariable. All right, so let's just dive right in. Notice these directions just ask me to find the critical points. They don't ask me to go further and identify anything. Just find the critical points. So step 1, what do I need to do? Right? I'm just looking for the suspects. Find partial x. So that's not too hard to do, right? My partial of x is what? 3x squared minus 3y. And then my partial with respect to y is also 3y, is a 3y squared, right? Minus 3x. So now this is where your algebra comes in. This is where you're going to have to do some algebra. It depends upon the system. Am I just going to add down? Are they all linear? Am I just going to add down, or am I going to have to do substitution? In this case, I looked at the first equation and I said, hey, there's a y to the first here. I went ahead and got that by itself, and then I substituted in for this y. I've substituted in, and I ended up with 3x to the fourth minus 3x is equal to 0. So I did my quick algebra, and I got x is either equal to 0 or 1. So I have two cases that I got to go get the corresponding y for, right? So I have x could be 0 or x could be 1. So I plugged those back in, and I got my y values. When x was 0, I got that y was also 0. When x was 1, I got that y was also 1. So those were my critical points. Double check that I didn't do any mistakes with my math, that they both do make the partials 0. And I'm done with this problem because all they asked me to do was identify critical points from the domain. And notice I don't have any domain issues, so I'm not worried about does not exist. Okay. Here's the picture of it. I guess this doesn't let me go to an outside website, but while I'm recording, boo. But if you click on this, it'll show you, you can clearly see that one of them is a minimum and the other one is a saddle point. But they didn't ask us to, but I just did want you to see it. But, oh well, I guess we can't see it. All right, so this next problem asks us to find all the critical points. So again, I'm not identifying maxes and mins, just critical points, but oh snap, they didn't give me the actual function. They just gave me the partials. So what's my next step? I don't do step 1 and step 2. They're already given to me. So my next step is step 3. And I just wanted to go through some different algebra with you on this one, right? So hopefully you can see it should be pretty obvious. Get the square root by itself and substitute into here. So I solved for root y and then substituted in and then did algebra. And I got my candidates. I only got one x candidate and it corresponded with the y candidate of 2. Verified that those did indeed work. 2 times 4 is usually 8, minus 6 is 2, minus the square root of 4, which is 2, and 2 minus 2 is 0. Negative 4 over 2 times the square root of 2, which would be negative 1 plus 1 does indeed make 0. So make sure they both satisfy, and then name your critical points. Right? So, and I only had one critical point, 4 comma negative 2. All right, now let's really get to work. So to determine, once I have my, oh, look at the teeny thing in the bottom. Determine if a critical, that must mean this slide is about to get really full. Determine if a critical point is a max min or a saddle point. How do I do that? So like I said, there is no first derivative test in multivariable. So I just have to use the multivariable version of the second derivative test for extrema. So think about this. We're going to take second derivatives, pure ones, fxx and fyy, not mixed. When you do that, what you're technically doing is you're thinking about the curvature along paths that are parallel to the x-axis or the y-axis only. That's what you're doing. You're thinking about curvature there and in both of those directions. If you find a mixed partial, which we're going to be dealing with continuous functions, so that would mean, right, that the partials are continuous. So fxy is going to equal fyx by who? What was that guy's name? Yeah, Claro. That measures and talks about curvature as you move along like a diagonal path, right? Some kind of, or paths that are not parallel to the x-axis and the y-axis. So we're going to use all of those second derivatives in a proof of how I figure out whether I can classify a critical point as a max, a min, local, or a saddle point. So if I do have a critical point, so this theorem depends upon knowing my critical points first, and I have second order partial derivatives that are continuous, at least continuous in a region that contains the point I care about, then I'm going to define this super D, right? Super second derivative, multivariable second derivative formula. Oh my God, look at that. So now kind of take the ABs out of it. You're taking the product of the pure second derivatives, and then you're subtracting the mixed partial, but squaring it. Okay? Now, before we think about why we would do such a thing or what these can kind of mean, let me just give you the conditions after this. So, oh my God. I'm going to highlight the last case first, because the last case is if our multivariable second derivative test is equal to 0, that's just like what I did in the warm-up, where if your partials are equal to 0 and your multivariable second derivative is equal to 0, we can't make a conclusion and we have to do something else, and that's not going to happen to us. Our goal here is to test using this second derivative formula. So notice the next three cases. The top two are when we end up with a positive value, and the third one is if we end up with a negative value. So I'm going to take care of that case first. If our multivariable second derivative test gives us a negative value, then we don't have to do anything further. We have a saddle point. Okay, we have a saddle point. However, if we get a positive value, we have to then look at one of the pures. And I'm going to write this as looking at fxx, but you could just as easily do fyy if you wanted to. If the second derivative overall formula is positive, and also the pure fxx is also positive, then I have a minimum. So I kind of think about this phase, right? D was positive, fxx was positive. I have a smile, and a smile is concave up. I have a minimum. Versus if the second derivative formula is positive and the pure was negative, then I have a maximum, where D was positive, fxx was negative, so then I have a little frowny thing, which is concave down, and I've got a maximum. Okay, so those are my memory tricks. You do you. All right, let's talk about why these things may be, and just not formal proof or anything, just kind of intuitive, right? So those are my conclusions. Well, here's what I think. Thought process. All right, there's some pretty pictures of a paraboloid that is obviously concave up everywhere, one that's concave down everywhere, and then a saddle point. But I have some paths highlighted. Do you see that? Oops, there's my little. So, right, if I follow this path, right, and notice this path is like parallel to the x-axis, right, follow this path, and really if I follow any path along there at this point, the concavity is in agreement. Same here, and this path I chose is parallel to the y, I think, right? Oops, my glasses. This one's parallel to x, this one's parallel, whatever, you get it. Anyway, no matter where I go, no matter what path I follow here, right, the concavity is kind of in agreement. So think about why that might be with this. If you have two values that you are multiplying together, and they have the same sign, both positive and both negative, this value here is going to be positive, right? And then you're subtracting a positive value and still staying positive, right? That's how D is positive. If that's true, then you've got this agreement. You've got this agreement in concavity all surrounding this point. However, if, oh, my little picture covers that up. If our D formula is negative, right, what that says is These two values disagreed. They were negative, right? One was positive, one was negative, and then you're subtracting a positive value, so you have a negative and then another negative. Our D formula is going to be negative, and it means that the concavity wasn't in agreement. It didn't agree, right? And that's what created this saddle point where, look, oh, along this path I feel concave up, along this path I feel concave down, along this point I feel, along this path I feel like a point of inflection, right? There's not enough agreement that creates the saddle point. So intuitively, what do I think? If my D formula is negative, it's because the partials, right, in the X and the Y couldn't agree, or they did agree, so they both were positive or they both were negative, but fxy, the concavity in the diagonal and the non-parallel to the xy planes, it was strong enough to throw off the agreement in the X and the Y direction, right? I hope that didn't make things worse for you, but that's kind of like generally intuitive what's going on with that big messy formula. Really, all you have to remember is that formula and what the conclusions are. So let's go. So example 3. Notice this one says find all local max, min, and saddle what? Values. That means they actually want the height. They're not asking you to compare and get global versus, get absolute versus local, but they do just want the heights. So there's my service. I know I have no continuity issues, so I'm not talking about having any partials that don't exist. So find the partials. Nice, easy partials to find. Set them equal to 0 for a system of equations, and then look how nice this algebra turns out. You're welcome. Welcome. So this algebra turns out so nicely. I have everything that's linear, and I'm just going to add those down. And, right, I'm going to get negative 2x is equal to negative 8. Therefore, x is equal to 4. Plug back in, and I got when x is equal to 4, y was 2. So I only have one critical point. There it is, when x is 4, y is 2. And now I'm going to use a handy-dandy table after I get my pure second derivatives and then my mixed derivatives. So again, these were pretty nice. So if I take fx and do my partial again, I get, with respect to x, I get negative 4. Fy, with respect to y, I get negative 2. And then I can do either mixed partial. Again, we have continuity. It doesn't matter whether you do fxy or fyx, but repeat with your partial with respect to y, and I get 2 either way. This one with respect to y, that one with respect to x, I get 2. And then I'm going to organize myself. I'm going to take any critical point, put it here. Then I'm going to copy down. Now, these are nice because they're constants, but sometimes remember our partial can be in terms of x, y, one or the other or both, and I'm plugging in my critical point to see if my pure and mixed partials are positive or negative or in their values. So I'm going to take, since these are just constants, I didn't have to plug anything in. Remember, I'm multiplying those two values together, and I get 8. And then I'm going to subtract this value squared. Oops, I already squared it. I was like, wait a second. Sorry, my partial is already squared. So I got 4. So 2 was squared and got 4. So I have x minus 4, which is positive. And I looked back at my pure partial with respect to x, and it was negative. So what does that mean? Now I'm going to classify them, right? D was positive, fxx was negative. So I have this frown thing, which means I have a max. And then because they asked for the values, plug 4, 2 into the function. So all the way back here, plug 4 in for x, 2 for y, 2 for y, 4 for x, 2 for y, minus 7. And I got 13 when I was done. Okay, so that one wasn't too bad because my partials were constants. I only ended up with one critical point to test and classify and then actually find the height. All right, this one, read again the directions. I'm not just finding critical points. I need to classify, but they didn't ask me for any values, so I don't need heights at all. So let's go. Again, you can pause the video if you want to see if how much of this you can get through yourself. There's my partial f with respect to x, my partial f with respect to y. Next step is to create a system of equations. I've got linear and quadratic, so I'm going to have to kind of think through my algebra a little bit, solve this system. I looked at the first equation. I pulled out 6x, and I got two cases. Y is equal to 1 or x is equal to 0. So I took each one of those cases and went back to the second equation. And I said, case 1, if y is equal to 1, if y is equal to 1, plugged it into the second equation. Oh, I don't know why that's blue. And I got x is equal to positive or negative 1. So I have a critical point 1, 1, negative 1, 1. Then I did case 2 when x was 0. Sometimes it's hard for me to see where my pen is. Case 2. When x is equal to 0, plug back in again to the second equation, and I got 0 or 2. That means I have a total of 4 critical points, right? Because I have when x is 0, y is 0, and when x is 0, y is 2. So, and again, I can't pop out of this this app to show you, but I have a link to what this surface looks like and in GeoGebra if you want to investigate. So here again is the surface that I found the partials and my critical points for. So now I get my pure partials and my mixed. 6y minus 6. Oh, look, my pures are the same. And of course I expected my mixed to be the same because we're dealing with continuity. So then step 4 is I remember my formula for the second derivative, multivariable second derivative test here. And then notice that I just plugged in, this time I've got fxx in terms of y, same with xyy, and then my mixed is in terms of x. So I'm going to have to plug some stuff in, right? So this time my chart is even a little bit more useful. So I put my critical points there in this column. I put my pure in this column, pure with respect to y in this column, then my mixed squareds here, and then what is my value of d. And then notice I don't have a fxy column over here because I just was asked to classify. So I just kind of wrote this all in one line. I've tested my first critical point, negative 1, 1. Plugged into fxx, plugged into fyy, plugged into fxy, and then squared it, and I got a negative. Since d was negative, I had nothing else to do. I have a saddle point. I did the same with 1, 1, and I got another saddle point. The next critical point, though, I plugged in 0, 0, and I got that the second derivative test was positive. So I can't stop there, right? I have to go back and look at either fxx or fyy, but you just have to be consistent. I looked at fxx. fxx at my point was negative 6. Right, which was negative. Therefore, I had d positive, negative, right? So I have my little frowny, so I have a local maximum. When I plugged in 0, 2, right, I had I did my second derivative formula, and I got positive, so again, I can't stop there. I looked at fxx, plugged in, right, 6y minus 6 was positive, greater than 0, since I already had d positive, check, and then fx was also positive, check, smiley face, which is concave up, therefore I had a local minimum. All right, so that's it. Try the homework assignment for this. There's a lot it's pretty straightforward but you do have to memorize a formula and what each condition is it needs to be met for your conclusion. Make sure you read your directions for, are you just being asked to find critical points? Are you being asked to classify and evaluate? Are you just asked to classify? Okay. All right. Well, we'll come back with another video later. Bye.